Alright, here we go. Welcome to Chapter 5 video lecture for physics. I'm going to go ahead and get started, and just like the last one, I'm going to plan to go relatively quickly with the idea that you can pause it and rewatch sections, and that we'll discuss some stuff in class. So let me do full screen action here. Okay, here we go. So we're going to start in Chapter 5 taking a look at everything we've looked at in Chapter 4, except now we're going to look in 2 dimensions instead of 1 dimension. So all of the force diagrams that you've been drawing, you now need to include both the horizontal and the vertical forces. And when you're looking at F net equals ma, you're going to have both acceleration that could be vertical and acceleration that could be horizontal. So before we can get to the complex force diagrams, we have to talk about 2D vector components. So this is something that you may have already seen in pre-calc, but if you're in pre-calc this year, then you probably haven't seen it yet, so I'm going to go through how to do vector components. Finally, we use friction as an example of 2D motion, and then inclined planes, which are a more complicated example of 2D motion. Alright, so what is a 2D vector? A 2D vector is just, well, you know from before that a vector is anything that has both a magnitude and a direction. So a vector includes direction like left and right or up and down. So up until this point, all of our vectors just pointed left, right, up, and down. There was nothing coming off at an angle. So the difference in this chapter is we're now going to allow things to come off at an angle, which means we have to break that vector that's at an angle into its components, and we're going to see lots of examples of that. Here we go. So when you have something at an angle, like this vector A here, A is the length of it, and this arrow represents the direction at some angle theta as measured from the x-axis. So let me bring my little pen here. So if we were drawing an axis, this would be the x-axis, and this would be the y-axis. So we're always measuring from the positive x-axis, and this angle is measured up from the positive x-axis. So you should know SOHCAHTOA already. So even if you haven't had pre-calc yet, all of you should have had geometry, and all of you have to remember SOHCAHTOA. So you can find the y component, which is opposite of the angle, using sine. So sine gives you the y component, which is opposite of the angle. So y component, sine. And the x component, which is adjacent to the angle, is going to be cosine. So cosine theta equals adjacent x over hypotenuse A. Cosine theta equals adjacent x over hypotenuse A. And if you solve this equation for x, simply multiply both sides by a. This a is going to move up over here. So you'll have a times cos theta on this side, and x on this side, rearranged slightly. And you get x equals a cos theta. Okay, so the adjacent side length equals the hypotenuse multiplied by cos theta. And you can do the same thing to get the opposite side length, y equals a sine theta. So there's a lot of symmetry here, right? The only difference is the x component is cosine, the y component is sine. So these are really important, and you should be able to go straight to these without having to write down sine equals opposite over adjacent every time. So you should definitely be able to go straight to these. Anytime you have a vector that's at an angle like this, and you want to get the 2 components, which is going to happen all the time, you just want to jump straight to x equals this, y equals this, and then it won't be a time waste for you. Okay, more examples. Paint it in. All right, yay. So let me give some example here. Let me change my color. So here's an example. Suppose you have a 30-degree angle, and suppose this is 10 newtons. So it's a force coming off at an angle, and you want to break it into its x and y components. So here you're going to have, let's call this F sub x. Let's call this F sub y. So this is the y component of the force, the vertical part, and this is the x component of the force. And we're going to jump straight to our shortcuts here. Fx equals F total, which is the hypotenuse. So maybe I should label this guy F total. So the length of the adjacent side here is equal to the total hypotenuse multiplied by, since it's adjacent, it's cosine theta. And so that's going to equal 10 times cosine of 30 degrees. And so I don't have a calculator in front of me, but you could type that into your calculator and get the answer. Likewise, Fy equals the hypotenuse, F total, multiplied by sine theta. And so you can plug in 10 times sine of 30 degrees. And I don't need a calculator for that one, because you guys hopefully know that sine of 30 degrees is 1/2. So this is 5 newtons. And actually, cosine of 30 is root 3 over 2. So this is actually 5 root 3 newtons. But that's going to equal like 8 point something. Anyway, the point is, if you have a vector at an angle, you can resolve it into its components. That's kind of the word that's often used, is resolve it into its components or break it into its components, which are along the x and y axis here. And anytime you have something at an angle, this is what you're going to want to do. And the reason you're going to want to do that is because once you have the x component, you can compare all the x components to each other and look at f net just in the x direction to figure out the motion side to side. And you can look at f net in the y direction to figure out the motion up and down. So it's really helpful. All right. Once you've broken everything into its components, how do you get the total of everything? How do you add them up, so to speak? So you're going to treat it just like we did with one-dimensional stuff. You're going to treat stuff going to the right as positive, stuff going to the left as negative. Although on your video that might have been just reversed, I don't know. Anyway, right is positive, left is negative, and then you add up the total horizontal forces to get the F net horizontal. Then you're going to have up as positive, down as negative, and you're going to add up the total, including magnitude and direction, in the vertical direction, and get the net vertical force. So at the end, you'll have 2 F nets, one up and down, and one side to side. And so then you can calculate the motion up and down and side to side independently of each other. So the two will be completely independent of each other. Side note here, vector subtraction is the same as adding a negative. Okay, so since negative means opposite direction, if you're subtracting two vectors, like say I've got vector A here, and I've got vector B right here, then A plus B means they're both going the same way. That's A plus B. And here's A minus B. So there's A minus B. So same length. Well, it's not exactly the same length, but you get the picture. That vector there, if I put a minus B, it just points the other way. So that's kind of cool. All right. The concept that you can use to help visualize this is called the tip-to-tail method. So that's what I've shown here. You just take this second guy that you're adding or subtracting and put the tip or the tail of him on the tip of him. So you just basically connect the arrows so that one of them ends and the next one begins. So here's some more pictures that will illustrate that. So you're starting off with vector A and vector B, and you're trying to find the sum total of these two vectors. What do they equal when you add them together? So you can do A plus B, or you can do B plus A. If you do A plus B, start along vector A. So move this way, and then immediately at the end of A, pick up and draw B. Now remember, the vector is the magnitude and the direction, but it doesn't matter where it starts. So you can visualize sliding this guy, which is his original location, slide him up here, and then redraw him with the same length and in the same direction, and it's the same vector. It doesn't matter where it starts. Vector is just magnitude and direction, but not starting position. So the total A plus B, here's where you started, here's where you started, and here's where you ended. So the sum total of A plus B is equivalent if you took this diagonal. So instead of taking path A and then path B, you could have just taken this overall straight path, A plus B, and all that matters is you start in the same place and you end in the same place. So the vector sum is at a different angle and a different length. It's like if A was 5 and B was 5, A plus B is absolutely not 10. It's actually going to be shorter than 10. And that's because the vectors don't point the same way. So when you're doing vector addition, if your vectors don't point the same way, when you add them up, it'll be less total length than if you just added the two numbers together. Hopefully that made sense. So this is the concept. I'm going to write that right here. Concept. So if I say conceptually, how do you add vectors? You say tip to tail, and you just visually look at it. Okay, I'm going this way, I'm going this way, so my total is going this way at a diagonal. Okay, but that's great if you want to kind of visualize what's happening or you're drawing a sketch. But if you want to actually mathematically calculate the direction or the length of the resultant vector, which is the sum of the two vectors, you're going to need to be more mathematical about it. And that's where those vector components come into. So here we've got different vectors. So ignore this side now. Start a fresh problem. Vector A is going up and to the right. Vector B is going down and to the right. And suppose you want to find the grand total of A plus B. Okay, you could use tip to tail. So you could draw this vector B right here. You could draw it in, and it's something like that, right? So your ending point is going to be something like this. But that's kind of a vague notion. Let's figure out exactly where it is. So vector A can be broken into a vertical component, A sub y, along the y-axis, and a horizontal component, A sub x, which is along the x-axis, horizontal. Okay? So instead of going along this diagonal, you could think about it as saying go straight up for some distance and then straight over for some distance. Likewise for vector B, instead of going along this diagonal, you could say go right this distance b sub x along the x-axis, and then go down this distance b sub y along the y-axis. Okay? So the net effect, if you were to walk along A, and then you were to walk along B, that would be the same as walking along AY, AX, BX, and BY, all four combined. So now you can isolate the vertical motion and the horizontal motion and look at the two separately. So let's just look vertical. First you walked up this distance AY, then you walked down this distance BY. So the net displacement up and down is up AY and then down BY. So you're going to do this upward one minus this downward one, and that's going to give you the total vertical displacement, y total. Okay, then you can imagine walking. First you're going to walk to the right, this distance, AX. Then you're going to walk to the right again, this distance, BX. So the total distance you walk to the right is BX plus AX. So the x total is the sum of these two all the way this way. And now you can say, okay, if I know I walked up a grand total this much, and to the right a grand total this much, how far away am I from the starting point? So this length here, how do you find this length? Okay, so here's a triangle. Let me highlight it in a different color here. Highlighter, nice. So this triangle, this is exciting. I'm getting better at PowerPoint function stuff here. So this triangle that I've just highlighted, this has a right angle right here. And so you know that this vertical length here is one of the two bases, and that's y total, right? And you know that this base here is x total, and you're trying to find the hypotenuse. So you're going to use Pythagorean theorem, which is a squared plus b squared equals c squared. I hope all of you guys know this. A squared plus b squared equals c squared is Pythagorean theorem. In place of a and b, you're going to plug in x total and y total, and that will allow you to get the hypotenuse, which is the total of vectors a and vectors b. So vectors a and b, they could be distances, so you could be finding the total displacement. They could be velocity vectors, so you could be finding the total velocity. They could be force vectors, so you could be finding the total force. It doesn't matter what type of vector they are, the way that you add them will always be the same, because they include both magnitude and direction, so the math behind them is the same, which is really, really convenient. Okay, so practice breaking vectors into components and adding up the components and then getting the resultant vectors using Pythagorean theorem. The last thing is, what about this angle? What if you wanted to know what direction you're going? Okay, to get this angle here, you know the opposite side and you know the adjacent side, so you can write that tan theta, remember tangent is opposite over adjacent. So in place of opposite, you're going to put in the y value, y total. In place of adjacent, you're going to put in the x total. And then you can solve for tangent by taking arctan of both sides, or inverse tangent. On your calculator, it's this little button, tangent, and then the little -1. If you have any questions at all about how to do arctangent or tangent inverse on your calculator, just talk to me in class. Here's another example, completely worked out, of how to do vector addition to solve an actual word problem. So I think maybe I'll let you guys read through this problem, look at what I've done. I've gotten components, then I've gotten the totals in the two directions, and then I've used Pythagorean theorem. And so try to read through this one on your own, and then if you have questions, maybe at the very end of this video, I'll solve it. Yeah, no, we'll do it in class. If you have questions, we'll do it in class. But for now, just try to read through this and make sense of it. Maybe even try the problem on your own. Actually, pause the video, try the problem on your own, and then check it against my solution. That's awesome. Okay, second topic of the lecture, friction. So we've already talked about it just briefly, especially when we're talking about tug of war in class, how friction provides a force opposite of the rope pulling you, and that will help you win. So now we're going to talk about it in a lot more detail, and not just talk about it as an abstract force, but actually calculate the numerical value of friction and see what factors it depends on. So Newton's first law taught us that everything in motion should stay in motion, but when you look around you at the world, you see everything coming to a stop, like really quickly. If you push something, it doesn't stay in motion, it slows down and stops right away. And so you might be wondering, well, what the hell, man? Newton said an object in motion should stay in motion unless acted upon by an outside force. So either he was wrong, or there's an outside force acting on stuff all the freaking time. And so, of course, it turns out that there is an outside force acting on things, and that force is friction. If ever you're able to find yourself in a frictionless environment, well, first of all, you'd be in a lot of trouble. Just imagine Bambi on the ice. It wouldn't be fun. But imagine for a second that you were in a frictionless environment, and you pushed something, it really would continue to move on in the same direction at the same speed forever until acted upon by an outside force. But on Earth's surface, we pretty much don't have any frictionless environments. The best we can do is approximately close to frictionless, like on an air track or something, or maybe an air hockey table. It's pretty frictionless. But the point is, in real life, most things have friction, so we observe things slowing down and stopping because of that friction. So what do we know about friction? We know that the direction that the force of friction points is always opposite of the motion. Right? Friction is never going to cause something to move. It's always going to cause them to slow down by pointing the opposite of which way they're going. And the reason it occurs is because these two objects, as they go past each other, they're rubbing against each other. So there's some kind of contact force between the two surfaces. And so that contact force depends on two factors. It depends on what the surfaces are made of, the type of material that the surfaces are made of, and it also depends on the force pressing the surfaces together. So just take your hands for a fun example, and just barely loosely touch them together so that they're barely touching, and rub back and forth, right? So there's some friction, you can feel it. Now push your hands together really tight and try to rub back and forth. And you'll notice two things. Number one, it's a lot more difficult to rub your hands. And number two, they start to warm up. And that's because of friction and energy. And we'll talk about the warming effect back in chapter 12, thermodynamics. But the idea that it's much harder to move past each other when they're pressed together makes a lot of sense in your daily intuition, right? The heavier the object is, the more gravity is pushing the object down into the ground, the harder it is to slide it forward. So pushing heavy things is harder than pushing light things because the force pushing them together is heavier, or not heavier, sorry, is stronger force. So the way that you can make things easier to push is by changing the surface, like, hey, throw it on wheels, or put some oil down in between the two surfaces that you're sliding, and then they'll glide a lot easier. Or you can decrease the force between the two surfaces by kind of lifting the object up a little bit before you push it. And again, I hope that matches your intuition and your life experience. Okay, I put here, can you think of some examples of surfaces with high friction and low friction? So pause the video, ponder that, and then we can talk about it in class. Alrighty, here's a nice force diagram depicting pretty simple overview of a friction problem. So you've got a box sitting on a table. It's like the most standard example that we use all the time. Of course, you have your long-range force gravity pointing downward, and the table is holding it up, F normal from the table holding it up, and these two will be most likely equal and opposite. Pretty much all the time equal and opposite. So that's your vertical direction. Same as we had before, vertical direction, F net. Again, practice your notation here like I was talking about in class. Practice writing F net as the upward force positive, so positive F normal, minus the downward force. So F up minus F down equals ma. So there's F net equals ma. But since the acceleration is 0, the object is not moving, it's not flying up in the air, and it's not flying down into the table, then F normal minus F gravity is 0, and therefore F normal should equal F gravity. Great. So now the interesting stuff is happening side to side. If you push the box to the right, for example, friction is going to oppose that motion and point to the left. So the force of the net force in the horizontal direction is, again, we're taking positive to be to the right and negative to be to the left. So F push is positive, minus, because it's to the left, force of friction. And that's going to equal ma, and we can even put a little subscript right here, ma horizontal. Or even better, let me make it even better, is to call this ma sub x. That's even easier, right? If you treat the horizontal axis as the x-axis, this is ma sub x. Okay, so the object, according to the picture that I have here, it's going to accelerate to the right because the force of the push is larger than the force of friction. So in a real problem, obviously, you'll be given numbers for all this stuff, mass of the object, etc. But your force diagram will look something like this, and then the numbers that you fill in will depend on your specific problem. Okay, so when you start calculating it, what are you calculating and how do you calculate it? The force of friction, we already said, depends on two things. It depends on the type of surface, and it depends on the force pressing them together. So the equation is going to have those two variables in it. So your force of friction equation is like this. Force of friction, and the first variable here, mu sub k, this is the Greek letter mu, mu, and it's a constant, and it's called the coefficient. Alright, let me write this. Coefficient of friction. So it's a variable in the sense that it's different for each material, but it's constant in the sense that for a given pair of materials, the value of mu will be constant. So for example, if you are sliding wood against wood, like two pieces of wood that are sliding against each other, then the value of mu will have some certain value. Or if you have two pieces of steel and they're sliding against each other, there will be some certain value for mu. So the value of mu is different for each pair of objects, but for a given pair of objects, it's the same no matter what those two, no matter what force is pushing those two objects together. So the second thing in the formula is F normal, which is the force pushing the two objects together. So typically, you'll have some kind of object sitting on a table or whatever. It's got F gravity down, messy handwriting, and it's got F normal up, and then it's got friction one way, right? Force of friction. So F normal is the force between the book and the table, for example. That's the amount of compression pushing those two things together. So the tighter you press those two things together, the more friction there is going to be. So force of friction equals mu times F normal. And this mu here, it has a subscript of a K, which stands for kinetic. Kinetic just means motion. So if the two surfaces are rubbing past each other, they're actually sliding past each other, you're going to use the value of mu kinetic, which you can look up in your book. For different types of materials, there's different values and they're listed in the book. On the other hand, sometimes objects are at rest, but there's still friction acting on it, right? So imagine you have some really heavy box, and you stand over here, and you push it, right? So you push really, really hard. This box then, it has a force on it, F of your push. But if the box is super big and heavy, right, you're not going to be able to push it because maybe you're not that strong. And so if there's a force to the right, but the box is not moving, you know there has to be a force to the left. So that force to the left is the force of friction holding it in place. So even though the box is not moving, there still could be a force of friction. Now, this force of friction, if you calculate the value by plugging in mu s times F normal, this force of friction might actually come out bigger than the amount you're pushing, okay? So the force of friction from this formula, this is going to calculate the max value friction can be. But static friction will never be more than it, quote, needs to be to keep the object at rest. So let me just throw some random numbers. Say the friction max is 500 newtons, okay? And say you're only pushing with 100 newtons. Well, the friction is not going to be 500 newtons because that would imply that the friction would be sucking the box over to the left. Okay, that doesn't make any sense at all. Instead, what happens is the value of the force of friction, it will match whatever you do to it. So if you push for 100, the force of friction will be 100. If you push for 200, the force of friction will be 200, all the way up to the max value. So you could be pushing at 500, force of friction will be 500, but as soon as you push at 501, the force of friction, it can't go higher than this value of 500. So when you push at 501, the box now has a net force to the right, and it will start to move to the right. And then, further point, as soon as the box starts to move to the right, now it's no longer at rest, so you have to switch from using mu static, which was what you were using while it was stationary, not moving, and you have to switch and now use mu kinetic. And interestingly enough, mu static, even for the same two materials, mu static has a different value than mu kinetic. Okay, so it's really important that once the object starts moving, you use mu kinetic, but up to the point where it starts to move, you should be using mu static. So be careful that you use the right value, whether the objects are sliding past each other or whether the objects are stationary. All right. That ends the section on friction. We'll probably do a lot more examples in class, or I might do another video with actual worked out examples, but that's the concept and the math behind it. And the last topic is probably the most complex, and that is inclined planes. But while it is complex, it's extremely useful, both because it's applicable in real life, as these pictures show, pushing a wheelchair up a ramp, skiing down a slope, riding a roller, what is that thing? A skateboard, down some kind of incline, driving things up into the back. Basically, ramps in general are all around you. And if you haven't noticed it, I encourage you to, next time you're out and about, just look around you and observe how many ramps there are and how many things there are at an incline and how many things are sitting on inclines. And then you'll realize right away, wow, this is, if you're interested in studying how the world works, understanding how inclined planes work is really useful and important. Okay. And in addition to that, it's a great physics topic because it makes you use everything you've learned so far, and it provides nice, robust problems. So we're going to have some steps to follow when you're doing an inclined plane problem. So it's anytime you have an object on a slanted hill. All right, I just talked about why it's important. It occurs in the real world, and it makes you educated citizens. So there's a 4-step process to solving these problems. Number 1, just like any other force problem, is you should draw a force diagram, obvious. Then you have to choose your coordinate system. But now you're going to draw your coordinate system inclined, and on the next slide I'm going to show you what I mean by that. Since you're going to have forces that are inclined at angles, you're going to need to break stuff into components. Anytime you have a force at an angle, you are going to break it into a component. And lastly, once you have the x and y components, you can apply Newton's law, which is F net equals ma, separately to the horizontal direction and the vertical direction. Yay! All right, let's take a look and see how it goes. First, let me show you how you do the coordinate system. So here's your normal coordinate system. You've got your x and you've got your y. Now, I want to show you what it looks like on an inclined plane. You're just imagining these same 2 perpendicular axes. But what you're going to do is you're going to take them and you're going to rotate them, right? So they're still perpendicular to each other. But now, what we were calling our horizontal axis is actually tilted a little bit, and what we were calling our vertical axis is now tilted a little bit. And so now let me go Shift F5. So now when you're visualizing this, you can think about an incline that looks like that, and then you could think about a box sitting on it, and then you could think about all the forces acting on this box. Maybe you've got a force because you're pushing it up the hill. F push. Okay, you've got a normal force. Now here's the key. The normal force is perpendicular to the surface, so the normal force is not vertically upward. Because our surface is at an angle like that, the force is actually going to be this way. F normal, perpendicular to the surface. Okay, we also have gravity acting on this object, but gravity acts straight down. Gravity doesn't act along some arbitrary axis. Gravity acts straight down. So in this case, gravity is going to be pointing straight down. It may not be perfectly straight down, but it's pretty straight down. Maybe a little at an angle, but it's certainly not along this incline here. And your incline is probably at some angle theta. And if you're pushing it up the hill, maybe there's even friction down the hill. Maybe there's some friction here. Okay, so why is having this inclined axis so helpful? The way I've drawn it with this axis inclined, the friction force, the push force, and the normal force, all 3 of those are already along an axis, either horizontally or vertically. The only one, I need to label this guy force of gravity. The only one that's not along an axis is the force of gravity. So the only one I need to break into its components is the force of gravity. Now, what if, let me go back, hold on. Let me go back and rotate this guy. If I would have kept him like that, now you can see, now the force of gravity is straight downward, which is along our axis, but the force of the push, the force of the normal, and the force of friction, all 3 of those are at some weird angle relative to my axes. So you have a choice. You could take all 3 of those forces and break them into components, or you could take this axis, rotate it, and then you only have to break one force into its components. So this is obviously a lot easier mathematically because you're only doing one vector component force instead of 3 vector component forces. Okay, so how do you take the vector components of this force of gravity? It's not as hard as you think, but it still requires a little bit of attention to detail. Sorry, let me choose a new color. Ink color. Let's choose blue. This vector right here needs to be broken into components which are perpendicular and parallel. So the vector components that we want are going to be, one of them is here, and one of them is here, and this is a right angle. So see if you can visualize that. So we're making a triangle with a right angle. The reason this is a right angle right here is because this is a right angle right here. So our vertical axis is this way, our horizontal axis is this way, they're just tilted a little bit. So this component right here, we're going to call FG parallel because it's parallel to the ground. And this one right here, we're going to call FG perpendicular because this axis is perpendicular to the ground. So we're going to call this the perpendicular direction, and we're going to call this the parallel direction. Okay, and to get these two components, FG parallel and FG perpendicular, you need to know one of the angles in this triangle. Okay, so let's use a little bit of geometry. This is a 90-degree angle. This is an angle theta, and the total of these angles in a triangle has to add up to 180. Okay, so if this is 180 and this one is 90, then this one here plus this one here has to be 90. So this one here is theta minus 90. So exciting. Okay, this angle right here is theta minus 90. So for example, if this was 50 degrees, this would be 40 degrees. If this one is 20 degrees, this one is 70 degrees. So I think you guys all can make sense of that. Now we have a right angle right here. This is a right angle also. So this one right here is a complementary angle to this one right here. So if this one is theta minus 90, this one must just be theta because they have to add up to 90. That's kind of cool. I've made a big mistake. Let me fix it real quick. This one is not theta minus 90. This one is 90 minus theta. Okay, let me go back and say that one more time. This one here is 90 minus theta. Let's check and see that that makes sense. If this angle was, say, 20 degrees, 90 minus 20 is 70. That one is 70. That makes sense. If this one is 30, 90 minus 30 is, say, 60. So a 30, 60, 90. So 90 minus theta is the correct answer. But this is right. It just didn't follow from my previous mistake. So if this angle here is 90 minus theta, then this angle here is also theta because they have to add up to 90. Alright, so what does that mean about FG perpendicular? That means FG perpendicular, this one here, is adjacent to this angle, and you know that adjacent is cosine, so it's going to be FG cos theta, and this one here, FG parallel, is going to equal FG sine theta, because it is opposite of this angle here. Okay, so that's how you get your two components. Once you have your parallel and perpendicular components, you can look in the perpendicular direction, and you want to get, here, maybe I have another slide. I do have another slide. You want to get F net in the parallel direction equals MA parallel, and you want to get F net in the perpendicular direction equal to MA perpendicular. Okay, so you're going to get all of these from your force diagram. You're going to look at your force diagram, and you're going to ask yourself which forces are in the parallel direction. So let's go back and look at it. In the parallel direction, which is along the incline, you've got the force of the push uphill and the force of friction downhill. Okay, so those two forces would go in right here, F net parallel. How about forces perpendicular? What forces are in the perpendicular direction? I'm going to go back. Okay, you've got the normal force upward, perpendicular, and you've got this component of gravity downward. Okay, so in the perpendicular direction, you've got one force up and one force down. These two, here and here. In the parallel direction, I already said you have friction, and I already said you have the force of the push, but there's actually a third force in the parallel direction. It's hard to see because he's down here, but you can't leave off this parallel component of gravity. Right? So when you're pushing something uphill, it's hard. Why is it hard? Because you have to overcome a component of gravity that's pulling it down the hill. So in the perpendicular direction, you have two forces, one up, one down. But in the parallel direction, you have three forces. One uphill, the push, and two of them are downhill. You've got friction downhill and you've got the force of gravity downhill, which explains why it's hard to push stuff uphill. You're not only overcoming friction, but you're also overcoming gravity. Okay, so you'll have a couple forces in here for the parallel direction, 3 forces in here for the perpendicular direction, and finally, based on the mass of the object, the angle, and what information they give you about the push or pull and the coefficient of friction, you can plug numbers in everywhere and solve for the unknowns. Oftentimes you're solving for the acceleration, and then you can use these acceleration values, oh yay, you can use these acceleration values to find Vf, or Vi, or A, or D, or T. So again, all your Chapter 3 stuff is going to come into play with the acceleration, and all of your Chapter 4 stuff is going to come into play with the force diagrams. Okay, let me just show you 2 more pictures of force diagrams, so you can just kind of get this feeling that yes, this is what they always look like. You pretty much always draw a triangle with a box on it, and then you label some forces. So here you've got a force uphill, here you've got a normal force, here you've got a force of gravity. Now this force of gravity is broken into its 2 components. One of the components is the perpendicular component. That's this one. This is FG perpendicular. And the other component, I drew it on my diagram, I drew it down here, right? FG parallel. They've drawn it right here. So they took this guy and they drew it up here. Is that okay? Yes, absolutely. Because remember that for a vector, it's the direction and the length that matter, but where you draw it does not matter. So I can draw it this long down here, and you can draw it this long up here, and they mean the exact same thing. Sometimes it's better to draw it up here because it's easier to see because it's coming off of your object. If you draw it down here, you might forget about it. So if you want to draw them up here, I'm more than happy to encourage that. So you've got the force of gravity broken into its 2 components, and the normal force and the force of friction. So this one is just like what I had drawn. Here's another example. Now this one is breaking one of the rules that I told you guys, which is your force arrows should start on the object and point away. So actually this one here, it would be nice if it was drawn over here, and this one here, it would be nice if it was drawn over here. But it doesn't really matter. It's just to give you the idea that you have to break vectors into their components. So this one, and this one are already along the incline and perpendicular to the incline. But again, this force of gravity right here, it's not along either the parallel or the perpendicular direction. And the way that you deal with stuff that's not along one of your axes is to break it into its components. So they've broke it into perpendicular component right here and parallel component right here. So I know this is getting repetitive, but I can't emphasize how important it is that when you have an inclined plane problem, you have to break any vector that's at an angle into its components. Let me show you one step farther. What if I had a force F push, and it was coming at some weird angle like this? Holy crap, like what do you do? It's coming at some weird angle. And say I told you the angle is 30 degrees, I don't know. Okay, this one is at an angle. It's not in the perpendicular direction, and it's not in the parallel direction. So the way that you have to deal with that is, you know what I'm going to say, you have to break it into its components. So you're going to have a component here along the x direction, and then you're going to have a component here along the y direction. So you're going to get this component, and you're going to get this component, and the net effect of these 2 components together will be equivalent to this angled force. But this one is great because you can put him right in here with this one in the vertical direction, and this one is great because you can put him right in here with the horizontal forces. So you have to take something that's not fitting into this structure that we want, which is perpendicular and parallel, and force it to fit that structure by breaking it into components. Alright, that's the grand total of the concepts that we're going to cover. So you've got vector addition using concept of tip to tail and mathematics of vector components. Then you've got friction, which is going to be the formula mu times the normal force. So it depends on the materials, the coefficient of friction mu. You can look that up in the book, different values for different materials. And then F normal is the force pushing the 2 surfaces together. And the force of friction always opposes the direction of motion, and its value can never exceed the maximum value. And finally, you've got inclined planes, where you take an axis and you tilt it, and then anything that's not along the parallel or perpendicular directions, you have to break it into components using what you learned in section 1 on vector components. Alright, so go ahead and make sure you fill out the form after you watch this video, and we'll talk about this more in class.